How can scientists get a clear look at objects in outer space? How can they search for planets that might orbit nearby stars? Telescopes have been used to study the heavens for over 300 years, but Earth based telescopes have a serious handicap. The atmosphere surrounding Earth interferes with almost all radiation reaching us from space. For example, radiation in the form of light from distant objects is distorted by the atmosphere, making stars appear to twinkle. Light is just one form of energy given off by stars. Stars also emit invisible energies, including radio waves, infrared, ultraviolet, gamma, and X-rays. Except for light and radio waves, almost all of this energy is screened out by the Earth's atmosphere. Early space telescopes. The first space telescopes were designed to observe these screened out invisible energies. As early as 1947, rockets carried instruments high into Earth's atmosphere to measure ultraviolet and X-rays. By the 1970s, telescopes mounted on satellites were observing these and other invisible energies. In addition to being unaffected by atmospheric distortions of visible light, space telescopes can observe other types of radiation that are blocked by the atmosphere. Instruments attached to the telescopes gather information and transmit it back to Earth. Early space telescopes include the International Ultraviolet Explorer and the Einstein X-ray Observatory, named after physicist Albert Einstein. Both launched in 1978. And the Infrared Astronomical Satellite launched in 1983. Today's space telescopes. In the 1980s, the National Aeronautics and Space Administration, NASA, began planning 4 space telescopes called the Great Observatories. The first of these, the Hubble Space Telescope, was launched in April of 1990. It was followed by the Compton Gamma Ray Observatory in April of 1991, the Chandra X-ray Observatory in July of 1999, and the Space Infrared Telescope Facility in August 2003. The Hubble Space Telescope, or HST, is designed to observe visible light and ultraviolet and infrared radiation. It's named after the American astronomer Edwin Hubble. He was born in 1889 and died in 1953. The HST, which is about the length of a large school bus, has a mass of over 11 tons. Its orbit around Earth at an average altitude of 370 miles or 600 kilometers lasts 95 minutes. Ground stations keep in contact with the Hubble as it orbits, and communication satellites also track it. The Hubble is a reflecting telescope. Light enters the telescope and strikes a primary mirror. It is then reflected back to a secondary mirror, which redirects the light back through a small hole in the center of the primary mirror. The light is then analyzed by one of the Hubble's scientific instruments. Some of the scientific instruments used on the Hubble over the course of its operation have been repaired, upgraded, or completely replaced during periodic service missions by astronauts aboard space shuttles. Among the instruments used on the Hubble have been a wide-field planetary camera, which photographed large sections of the sky as well as the planets in our solar system, and a space telescope imaging spectrograph, STIS, which analyzed the light from an object in space to determine what elements it was made of, how fast it was traveling, and if it was moving toward or away from the Earth. The Hubble has given astronomers some of their most detailed pictures ever of various celestial objects. These range from planets in our own solar system to galaxies over 10 billion light years away. For example, the Hubble has captured images of giant storms on Mars, collisions of distant galaxies, the birth of young stars, strangely shaped regions of swirling dust and gases, and the evaporation of a gas planet closely orbiting a distant star. And in 1994, Hubble captured remarkable images of comet Shoemaker-Levy as fragments of its nucleus collided with Jupiter. The Compton Gamma Ray Observatory. The Compton Gamma Ray Observatory was designed to detect gamma rays, the most powerful or energetic form of electromagnetic radiation. This space telescope was named after the American physicist Arthur Compton. Because gamma rays do not penetrate Earth's atmosphere except at extremely high energies, they cannot be detected by ground-based observatories. Gamma rays can signal events such as the death of a star and provide information about black holes, pulsars, and quasars. Quasars make up the most powerful class of objects yet discovered in the universe. The Compton weighed nearly 17 tons. It orbited Earth at an altitude of about 280 miles. 3 of the Compton's 4 instruments were each about as large as a subcompact car. The size of the instruments is very important in gamma-ray astronomy. Gamma rays are detected when they interact with matter, so the number of gamma-ray events recorded depends on the size of the detector. The Compton Observatory made the first comprehensive map of the entire sky. It also discovered the nearby remains of a recent supernova and a new class of high-energy gamma-ray sources called gamma-ray quasars. The Compton completed its mission in 2000 when it re-entered Earth's atmosphere and burned up. Chandra X-ray Observatory. The Chandra X-ray Observatory was named after the Indian astrophysicist Subrahmanyan Chandrasekhar. The Chandra is designed to study sources of X-rays, including stars, exploding stars, called supernova, and matter falling into black holes. X-rays from celestial objects are focused by mirrors inside the Chandra and directed at special instruments. These instruments include a high-resolution camera to record the number and strength of the incoming X-rays in various spectrometers to analyze the spectrum of the X-rays. Among Chandra's discoveries were a massive black hole swallowing material at the center of the Milky Way galaxy, pulses of X-rays emanating from the polar regions of Jupiter, and an immense rotating disk of extremely hot gas moving through a distant galaxy. The Chandra also found signs of hidden dark matter, which may make up most of the mass of the universe. The Space Infrared Telescope Facility. The Space Infrared Telescope Facility, SIRTF, is designed to detect the infrared radiation given off by celestial objects. These objects include those not easily seen in visible light, such as small, dim stars, or forming planets hidden by thick clouds of dust and gas. The SIRTF's scientific instruments include a reflecting telescope, an infrared camera, an infrared spectrograph, and a multi-band imaging photometer. Because the SIRTF is sensitive to heat, it is shielded from the sun and the earth, and a special device called a cryostat, I think that's what that is, uses liquid helium to reduce the temperature of the equipment to about negative 459 degrees Fahrenheit. Other space telescopes. Other telescopes have been launched into space. 2 are operated by the European Space Agency. The International Gamma-Ray Astrophysics Laboratory, Integral, will make various X-ray observations and create a gamma-ray map of the entire sky. The X-ray Multi-Mirror Mission, XMM Newton, uses 3 X-ray telescopes, each with 58 mirrors, to detect the more X-ray sources than other orbiting observatories. A third, the High Energy Transient Explorer, HETE-2, is jointly operated by the United States, Japan, France, and Italy. It is designed to detect bursts of gamma rays as well as survey X-ray sources.